In this video, we're going to look at two questions on the topic of wave reflection and wave refraction. Okay, so let's look at the first question. It says a thin film of transparent material of refractive index 1.52 and thickness 0.42 nanometers forms a thin coating on glass of refractive index 1.6. It is viewed by reflection with white light at normal incidence. What visible wavelength in cool or vacuum is most strongly reflected? Okay, so the idea is that there's two layers for this thin film refraction or reflection. The first layer is some kind of material. And the second layer is glass where the refractive index is 1.6. And then the idea is that there's a white light ray coming through, and then it's reflected off the surface, and also at the same time it is refracted to the next layer, where it gets reflected again, and then parallel out. And then the idea is that because the next layer has a higher refractive index, then for this light ray, it will have a phase difference of pi radians, and then for this light ray, it will also have a refractive index of pi radians, and they essentially cancel out with each other. So in this case, we only have to consider this. Let's say this is the thickness, and the thickness is given in the question, which is 0.42 nanometers. Then the idea is that twice the thickness, which is essentially the total path taken by the second light ray, is basically equal to the order of image times the wavelength of the material, of the wave, sorry. So, however, there's another thing we have to consider, which is that wavelength in the material is different. And in this case, N2 over N1 is equal to lambda 1 over lambda 2. And N2 is the refractive index, while lambda 1 is basically the lambda in air. And this is lambda that we want. So the idea is that lambda is basically just equal to lambda air over lambda over refractive index. Now, how do you apply this equation? The lambda in the equation is basically the wavelength of light in air or the vacuum. So we can basically just time the refractive index to the other side. So that will be equal to this. And so what we have to do right now is to calculate out the left side of the equation. And this will be about 1.28 times 10 to the negative 9 meters. There might be a problem here. So this is basically equal to 1.9 nanometers. Because the wavelength cannot be shorter than 400, right? Because it has to be visible wavelength. Okay, I've checked the mark scheme. Yeah, so there is a typo over here. This should be micrometers, or else it will be impossible. So over here, this would be 10 to the negative 6 and 10 to the negative 6. So basically times by 1,000, which gives us 1280 nanometers. Okay, now, so the idea is that we want the most strongly refracted wavelength. So 1280 is definitely very big because for visible, it has to be between 700, well, approximately, and 400. So let's see. So the first try will be m is equal to 1, which is equal to this, and this is impossible. Over here, lambda is equal to 2, where the order of image is equal to 2, and that will give us 640 nanometers, which is actually possible. Now, we can actually go further. And it will actually work out to be something like 400 something nanometers. However, there is an idea that the lower the order of image, the greater the intensity. Same as white light in the refraction grating. And then so we don't have to do any further calculations. And so the question wants to do visible wavelength, and this will be the answer to the question. Now let's see the second question. So the second question is a lot longer, and it says a thick bottomed cylindrical glass beaker is placed on the bench. Water and oil are poured into the beaker and form discrete layers, as shown in figure 1. The bottom beaker is 1.8 centimeters thick, and the water is 1.2 centimeters deep, and the oil layer is 0.8 centimeters deep. The first component of the question wants us to draw a diagram showing the path of a ray at a small angle to the normal, traveling from the underside of the beaker and being refracted through the layers. Over here we're given a diagram. Okay, so I'm going to draw a diagram for myself as to make it a bit bigger. And then there is 3 layers. Okay, so this is 1.8, I think. Yeah, 1.8, 1.2, and 0.8. Okay, and it's glass, water, and oil. So the idea is that a light ray will start from here, let's say. And then water has a lower refractive index than glass, so therefore it will bend away from the normal slightly. And then it's the same for oil, away slightly, and then away slightly. Okay, so this is the trajectory of a light ray. Now that is component A done. Now let's see component B. It says, assuming the angles of deviation of a ray are small, calculate the apparent vertical displacement of the lab bench when viewed from above. And so that's viewed from above. And then it gave us the refractive indices, which are 1.5, 1.3, and 1.1 for glass, water, and oil, respectively. Okay, so let's see. How do we calculate the difference in height? I'm going to mark on this diagram, okay? So over here, this is essentially the last array, so let's trace this back over here. So this is essentially the apparent image of the object. Initially, the object is over here, let's say. No, so essentially, this is what we want to calculate. This would be the height. And then, how do we do this? We have to utilize the angles, okay? That is at least my idea. So over here, let's say this is theta 1, and then this is at right angle, so therefore this is theta 2, theta 3, theta 4. These are the angles, and we have to somehow link these angles to the length. Okay, I have an idea. So basically you can use like trigonometric ratios in this case. Now the problem is basically how do we link all of these variables together. I'm thinking of tan. Let's say this side is x, and then this is essentially y. Okay, so let me see. What we know right now is h plus y is equal to total thickness, which is 0.8, plus 1.2 plus 1.8, which is equal to 3.8 centimeters. And then another thing that we know, okay, so I'm seeing that this angle is also theta 4. Okay, so theta 4, tan of theta 4 is equal to x over y. Now let's see. Another thing that I'm seeing is this, okay? So we can consider this thing as a triangle. And then, yeah, this is my idea of utilizing the other angles. So these are triangles, right? My idea is that if we actually add the length, this length, this length, and this one together, we get x. So this is rather useful, and actually, we know this is, we know this side, and we know this side, and we know this side from the thickness or the depth of each of the liquids. So this will be really helpful, and this actually utilizes tan as well, which is we might be able to cancel out some terms. Okay, so the idea is that x is equal to, because tan of theta is equal to the blue one divided by the red one. So therefore, essentially what we can do is that we time it by the red one. So this will be 1.8 times sine of, not sine, cosine. Now tan of theta 1 plus 1.2 tan of theta 2. Okay, this is excellent, and over here we can actually see something. So if we actually link these two equations, we get y tan of theta 4 is equal to 1.8 tan of theta 1 . And this is the equation. Now, in order to calculate y, we have to know the values of the angles, or maybe cancel them out. In this case, what I'm thinking is that we might be able to utilize Snell's law, because this is essentially a process of refraction. However, from Snell's law, we can only know the sine of that angle. We can't know its cosine or tan. So assume the angles deviation rate are small. Okay, so this is a very important piece of information. It's the idea that the angles deviation rate are small, so therefore we can actually utilize this idea. If the angles are really, really small, then tan of theta is approximately equal to sine of theta. And we can actually utilize over here. So yeah, if we actually rewrite this entire equation, this will be y sine of theta 4 . Wait, I actually think I got some values wrong. Yeah, this one, okay, a bit of a mistake over here. It's supposed to be 0.8. Okay, so this is a more refined version of the formula. Now we can use Snell's law to express these values in terms of theta 1. So first what we know is that Snell's law. Now we apply this. So what's given in the question is that 0.5, 0.3, and 0.1. So and over here this will be 1.3 divided by 1.5 is equal to sine of theta 1 over sine of theta 2. We want to express the sine of theta 2 in terms of sine of theta 1. So therefore sine of theta 2 will be equal to and then in the same case, following the pattern, this will be then finally for sine of theta 4 following the pattern, this will be if we continue, we have to apply all of these back to this equation over here, and then so y, we have to express them all in terms of theta 1, and then we can essentially just cancel them all out. Theta 1 is just theta 1. Sine of theta 2 is 1.5 over 1.3. What I'm doing right now is that I'm already canceling out all of the sine of theta 1 is this. Excellent, so therefore we can actually derive y. So this will be equal to, I'm going to utilize the calculator. So and this gives us 2.85 centimeters, and therefore we will be able to calculate h, which is equal to 3.8 minus 2.85, which is suppose 0.95 centimeters, and this will be the answer to the question.